lecture we are going to discuss systems with constraints. We will study problems with constraints which we have avoided till now. We are going to look at the method of Lagrange multipliers and derive the equation of motion in that scenario. Till now we had been discussing problems where we had the system in a potential field. We followed the Hamilton's principle and derived the Lagrange's equation of motion. Then we discussed systems with non-potential forces or non-conservative forces, and we had the Hamilton-Ostrogradsky principle, and we had derived the Lagrange's equation of motion. In very many problems we have constraints which cannot be replaced. That means, I cannot reduce the dimension of the system further, because it may be because the constraints are non-integrable, they involve the rates of the coordinates. It may also be because it may lead to a complicated Lagrangian. Therefore, in such situations we have to deal with the constraints separately. There arises another situation where we need to deal with constraints separately, not include it in the or reduce the Lagrangian using the constraint, in situations where we want to find out the constraint forces, and I am going to demonstrate these things with an example. Consider this example of a simple pendulum. I would like to start with this example because this helps us understand why we need to sometimes work with coordinates which are physical coordinates, which are not the generalized coordinates. And in the pendulum example, we have always been looking at the angular coordinate as a generalized coordinate. What happens if we use the physical coordinates? Can we not proceed? Let us see where we get stuck. We have the physical coordinates x, y, with the constraint that x square plus y square must be equal to L square, where L is the length of the pendulum. We can write down the Lagrangian straight away. This kinetic energy, half mass times velocity square, which is x dot square plus y dot square, and the potential energy for this pendulum is mgy. X axis is the datum, and we write down the Lagrangian as kinetic minus the potential. Here I have written out, there is a correction in red, for kinetic minus the potential energy, that is a Lagrangian. With this Lagrangian, we are going to use Hamilton's principle, which gives us this variation of the integrand, and when I operate the variation operator on x dot square, it is x dot delta x dot and 2 times, that half cancels that 2. We have gone through all these steps. We have the boundary terms, and remember that at t equal to t0 and t1 our variations are 0, of course. So, variation in x is 0, variation in y is 0. And what do we have in the integral? We have negative of mx double dot delta x plus this term times delta y, and that integrated over time, that must be equal to 0. This is application of Hamilton's principle. Boundary terms vanish because the variations are 0 at the 2 time boundaries. Therefore, we are left with this equal to 0, this variation equal to 0. Now, what was our standard argument from here? Our argument was that the virtual displacement, the virtual displacements are arbitrary. This was our argument, the virtual displacements are arbitrary. But when we are talking in terms of physical coordinates where we can have constraints, actually we do have constraints in this case, x and y are not arbitrary, because they are connected by x square plus y square is equal to L square. Therefore, delta x, the variation in x, must also be related to variation in y. It is not arbitrary, both cannot be taken arbitrarily. You can take one of them arbitrarily, but the other one you can calculate from the constraint. So, this is what our argument is, this is where we get stuck. we do not have the liberty of saying that delta x and delta y are arbitrary. They are not arbitrary, they are not independent variations, they are not independent virtual displacements, they are connected by the constraint. How they are connected by constraint? If I take the variation of the constraint, this is what I will get, 2 times x delta x plus 2 times y delta y equal to 0. This is the connection between delta x and delta y, and that comes from our constraint. This is our relation between delta x and delta y. We could have replaced one in terms of the other and written the whole thing in terms of a single independent variation or virtual displacement, but we are not going to do that. What we are going to do instead is introduce Lagrange multiplier. We are going to introduce this constraint using Lagrange multiplier into our variation, the integral on the top. We will introduce this Lagrange multiplier. Every constraint must have a corresponding Lagrange multiplier. We introduce this, we multiply the constraint with the Lagrange multiplier. This is an unknown as yet, and very soon we are going to determine that. This is an unknown, and this Lagrange multiplier times the constraint we have introduced into our variation. This Lagrange multiplier is an unknown, and delta x and delta y are variations which are connected. Let us see how we can argue. This is our variational statement now. I collect terms of delta x and delta y. We have this delta x here, and it comes into our delta x equation using the Lagrange multiplier. Similarly, we have a contribution in the delta y equation using the Lagrange multiplier. The constraint has been completely absorbed in our system. Now, we will argue this way. Let us choose some lambda star. You see, delta x and delta y are not arbitrary, but what I can do is I can do away with one of these bracketed terms. There are two bracketed terms, one corresponding to delta x, the other corresponding to delta y. I will do away with one of the bracketed terms, so that I do not even have to worry about the variation of that coordinate. Let us choose lambda, some lambda star, such that the first bracketed term goes to 0. The first bracketed term goes to 0 as shown here. I choose lambda star so that the first bracketed term goes to 0. Then what I am left with? I do not have this, this goes to 0. So, the whole term drops out from my variation. Now, what is left is this, and in this I will say delta y is arbitrary. Therefore, if the integral is to vanish, the coefficient of delta y must vanish. Now, this is what we are left with, and here delta y can be chosen arbitrarily. If delta y is arbitrary and the whole integral must be 0, then the coefficient of delta y must be 0. Now, this is an argument, the whole argument broken in two parts. First, we said we just removed that first term which was multiplied with delta x. We just removed it, so that we do not have to worry about the variation in delta in x or the virtual displacement in x. We do not have to worry about that at all. We have chosen lambda such that the first bracketed quantity goes to 0, and what we are left with, that integral, if it has to be 0 for arbitrary delta y, then this must be 0, this coefficient of delta y must be 0, and this gives us the two equations. These are the two equations, but now it involves a third thing, the lambda. So, two equations, now three unknowns, but remember we have the constraint. These are equations in three unknowns, two equations and three unknowns, but remember we also have the constraint, that is also an equation. that also has to be satisfied by x and y. This completes the system. We have 3 equations and 3 unknowns x, y and lambda, but now observe that these are differential algebraic system. This is a differential algebraic system. We can simplify this further. This set of differential algebraic system completes the dynamics of the system, but this is not a very convenient form of the dynamics. What we are going to do is, in the next step we are going to determine the Lagrange multiplier and eliminate it from the equations of motion, and we hopefully will get some tractable differential equations of motion. The steps involved are as follows. We time derivate the constraint. We will time derivate the constraint 2 times. Why? So that we have x double dot and y double dot. Using those 2 equations of motion, differential equations of motion, we will eliminate the accelerations and solve for the Lagrange multipliers. We will solve for the Lagrange multiplier. In this case, we have only one Lagrange multiplier. We will solve that Lagrange multiplier and substitute that back into our equation of motion. Now, this, because we have derivated the constraint 2 times, we have got up to accelerations which we have eliminated using the differential equations of motion. Therefore, our Lagrange multipliers will be function of displacements and maximum velocities. Accelerations have been eliminated. And once I solve for the Lagrange multiplier, I will substitute that in the expression in the equations of motion, and this is what I am going to now show you. What has to be done? First, we differentiate the constraint. This is the first derivative of the constraint, this is the second derivative of the constraint. This involves x double dot and y double dot. This I will replace using the first 2 equations. I will solve for x double dot from the first equation and y double dot from the second equation and substitute. The first equation, x double dot is lambda by m x, and we also can find out y double dot. I substitute this equation 2, these 2 equations in equation 1. This is what I get: algebraic steps, straightforward algebraic steps, and I solve for lambda. Here you will find lambda is in terms of y, x dot and y dot. Once I have this Lagrange multiplier expression, I can substitute this back into the equation of motion. I substitute this Lagrange multiplier in the equation of motion, and this is my set of equations. Now, these are completely independent, self-standing equations of motion. 2 equations in 2 unknowns. Lambda has been eliminated. 2 equations and 2 unknowns I should be able to solve, but then there is a catch. Can I, for example, specify x and y independently? Of course, I cannot. Can I specify x dot and y dot independently? I cannot. Why? Because they are all related by the constraints, remember. Therefore, even though we have obtained 2 equations in 2 unknowns, solving them or setting the initial conditions is yet another step. What do? We have 2 second order ordinary differential equations coupled. To set the initial conditions, we need 4, let us say 4 initial conditions. At time t equal to 0, I need x at 0, y at 0, x dot at 0 and y dot at 0. These are not independent. We must satisfy x naught square plus y naught square as L square, because the starting point of the bob must be with the string taut. Similarly, the velocity, I have derived the velocity expression, and this is straightforward substitution of these initial conditions in the velocity expression. And remember, how did we find the velocity relation? We time derivated this. We obtained x x dot plus y dot equal to 0, and that is what we have x naught v x naught plus y naught v y naught equal to 0. Therefore, finally, out of these 4 conditions that I am considering, there are 2 constraints. Therefore, we have independent choice of only 2 of these parameters. So, there are 2 independent initial conditions, and now with these 2 differential equations and with these 2 these initial conditions and this constraint on the initial conditions, we have a complete system. Now, this I can integrate and find out x y location of the bob. Now, we generalize this this approach. Let us consider physical coordinates r 1 to r m. We have m minus n constraints. Now, this has been chosen so that we have n generalized coordinates, and here we consider m minus n holonomic constraints, which are rheonomic, which means they involve time in general. We will deal with non-holonomic constraints separately. Now, Hamilton's principle says the variation of the action must be equal to 0, and that gives us this statement, variational principle, and we have this as our Lagrange. This is the variational statement, and in terms of the Lagrangian, we have done these steps. We have put the boundary terms to 0. So, all those things have been taken care of. So, this is our variational statement in a simplified form, where we have pulled out this delta r, the virtual displacements in the physical coordinates, out of the bracket. But these delta r's are not independent, remember, because we have constraints. I have now written this dot product in a detailed form. For example, this first term is corresponding to the first generalized first physical coordinate, variation in the first physical coordinate, or the virtual displacement in the first physical coordinate direction. And similarly, this is the mth physical coordinate, variation in the mth physical coordinate, and this is the coefficient. Now, this delta r1, delta r2, delta rm, these are not independent because of the constraints that we have. Then what we do, so this is our variational statement written in a detailed form. These are subjected to these constraints, delta C1 equal to 0, and what is delta C1? Remember, these are rheonomic constraints, they involve time, but variation will not derivate that time. So, only we have del C1, del R1, delta R1 and so on up to del C1, del Rm, delta Rm equal to 0. So, this is the variation of the constraint, and like this I do variations for all the m minus n constraints. And then the next step is to introduce these constraints into our variational statement using the Lagrange multiplier. For every constraint I need one Lagrange multiplier. What do we do then? For every constraint, for every j, I have lambda j. Therefore, this I multiply by lambda 1 and so on, then lambda 2, and this I multiply by lambda m minus n, add them and introduce in the variational statement. Then we collect the terms of delta Ri. So, this is our statement. Now, we collect terms of delta Ri. So, this I have done, I have collected. So, this is written as a summation over I. In delta Ri, when I have to pull out delta Ri, correspondingly in that equation I will get this contribution from the constraint and the Lagrange multiplier. These steps you have to do yourself to understand. Now, because these delta Ri's are not independent variations, therefore, I cannot say that these bracketed quantities must vanish individually directly, though finally it turns out to be that, but the argument is in a different way. You have to understand this argument. What we say is we choose the lambdas, such that from 1 to m minus n, these many bracketed terms vanish. Here the summation is from I equal to 1 to m. In other words, something delta R 1 plus something delta R 2 and so on, something into delta R m minus n plus something into delta R m minus n plus 1 and so on, something times delta R m. This is the complete summation, goes from I equal to 1 to m. Now, what I am saying is I choose these m minus n lambdas such that the first m minus n brackets just vanish, which I can always do. I have to vanish m minus n bracketed terms using m minus n lambdas, which I can always do, provided some regularity conditions are satisfied. Okay, let us say that these regularity conditions are satisfied, so that the first m minus n bracketed terms they go to 0, and I have chosen these lambdas are special values for which these first m minus n bracketed quantities go to 0. What happens to the rest from m minus n plus 1 up to R m? What happens to these? Now, these can be independent variations, these can be independently chosen, and they are independent variations, therefore, each of those bracketed quantities must be 0. Therefore, from m minus n plus 1 to m, I going from m minus n plus 1 to m, the integral 1 will vanish when these coefficients vanish. In other words, these coefficients of delta R m minus n plus 1 to delta R m, these are the coefficients for I equal to m minus n plus 1 to m. These are n equations. Therefore, finally, what we have is the m minus n equations, which were vanished by choice of m minus n lambdas, and the rest of the n equations were vanished because the variations were arbitrary. Together they form the complete dynamics, but now this is not complete in that sense, but the equations of motion we have obtained, but it involves this m minus n lambdas which are not known. Therefore, we have not yet closed the system, but remember we have the constraints, we have these m minus n. So, we have right now we have m equations in 2m minus n unknowns. How 2m minus n unknowns? Because we had m unknowns plus m minus n Lagrange multipliers, and that is how I get 2m minus n unknowns, but equations are only m because there are m physical coordinates. But it is not to be forgotten that we also have the constraints with us, exactly m minus n constraints, and that will close the whole system. So, we have all the required equations and to solve the whole thing. We can solve for the physical coordinates as well as the Lagrange multipliers. Therefore, finally, we have 2m minus n equations in 2m minus n unknowns. So, we have a closed system, but these are differential algebraic systems and not very easy to handle. Therefore, we follow the steps that we have discussed for determination and elimination of the Lagrange multipliers. What do? We time derivate the constraints 2 times. Each constraint we time derivate 2 times to come up to acceleration, so that they involve accelerations. Then we use the differential equations to eliminate the accelerations and then solve for the Lagrange multipliers. Once we have solved for the Lagrange multipliers, we substitute these expressions back into the differential equations, and then the differential equations become standalone. They involve only the physical coordinates, but then in order to integrate, we process further, we need initial conditions, and for those initial conditions we have discussed methods of finding the initial conditions using the constraints, so that the initial conditions do not violate the constraints. Therefore, we have to look for the relation between the various coordinates at time t equal to 0, so that the constraints are satisfied at time t equal to 0. Further, the velocities must satisfy the velocity relations which are obtained from the constraints by single time derivative. So, to set up the initial conditions, we use the constraints and its derivatives, and their derivatives we have 2m initial values, m for each coordinate. So, we have these displacements, the position value, the m position value and m velocity values at time t equal to 0. Therefore, we have 2m initial conditions, but these are not independent. Why they are not independent? Because these initial, for example, initial displacements, initial position, that must satisfy the constraints. Further, the velocities must satisfy the constraints. The initial position therefore must satisfy all the constraints, the constraint vector. So, m minus n of these constraints must be satisfied by the position vector at t equal to 0. Similarly, the velocity initial velocity v naught must satisfy this constraint, which is obtained by time derivating the constraint. These are additional m minus n relations. Therefore, we have 2m minus 2m minus 2n. So, it is the summation of this and this. So, 2m minus 2n. Therefore, 2n independent initial conditions. We had n generalized coordinates. Of course, we did not work with generalized coordinates, but we had n generalized coordinates. We get second order differential equations in the generalized coordinate. Therefore, we will require 2n initial conditions, and that is precisely what we are getting. But we have worked with the physical coordinates. We have worked with the physical coordinates and obtained m ordinary second order differential equations, and the initial conditions we have 2n independent initial conditions. So, we have discussed how to eliminate the Lagrange multiplier in the differential equations to obtain all the differential equations. We have a self standing set of equations involving only the physical coordinates, and the initial conditions must be chosen carefully, satisfying these constraints. So, that completes our discussion on Lagrange's equation with constraints. So, let me summarize. We have looked at problems with constraints. We have introduced these constraints in our variational statement using the method of Lagrange multipliers, and finally, I have discussed how to obtain the equations of motion, how to eliminate the Lagrange's equation using the constraint, and very importantly, how to set the initial conditions of the system, satisfying all the initial conditions, satisfying all the constraints in terms of the displacement as well as the velocity. So, with that I will conclude this lecture.